All right. Good morning, everyone. Hope you're all doing well. Before I get going with the review of Introduction to Machine Design that we started last Tuesday, I really would like to extend a thank you message and appreciation for everyone who is helping us to be here comfortably and safe and enjoy the face-to-face meeting. I thank you for your compliance with the university direction and expectation to respect and protect each other by doing this extra mile sacrifice of using a mask, even if we're not convinced, but we're just doing it in respect to each other. So I really thank you and appreciate that. I have to tell you, it makes me more comfortable being here and able to continue our mission. So thank you very much for your sacrifice. On Tuesday, we started by looking at mechanical material characterization, specifically Young's modulus of elasticity. We talked about the simple tension test, the stress strain diagrams. We looked at shear modulus. We looked at Poisson's ratio. And today we're going to continue with strength and stress. And many times these two terms get confused together. Is there a difference between a strength and a stress? What's the difference?
Between strain and stress. Stress is the amount of force or pressure put on an object, whereas strain is the amount of
Yeah, I meant to say strength and stress.
Strength. Strength is how much stress it can hold in its entirety.
Very good, very good. So really, strength, when we refer to strength, it's a property of the material or a mechanical element. So this is how much it can handle. And this is what we identify from running a simple tension test. And of course, we do not just run one simple test, but we run many of them, and then there is a statistical study before that strength is being reported. Like when you go in the back of the book and you pull the strengths, whether it's ultimate strength or yield strength of a material, this is not a result of one test, but this is based on a statistical study that come up with this recommended strength value. The strengths may be affected by treatment or processing, unlike the modulus of elasticity. So this could be affected by treatment and processing. It may or may not be uniform throughout the parts. There could be some slight variation. On the other hand, a stress is really a state property at a specific point. And I really want to emphasize that. You've been calculating stresses in solids, in intro to machine design, and we also used to calculate internal forces. Can someone help me understand the difference between internal force and stress? How would you describe the difference? They're related for sure. And we usually say, oh, we use the method of sections, we cut, and we start looking at the internal forces. How are they related? How is the internal force related to stress? Excuse me? Yes, stress is force per unit area. And internal force is a force. Yes, it could be a moment, like bending moment as in beams, correct? And with that being said on an area, I can tell you that the internal force is a resultant of the stresses applied on that section. So the stress is applied at a point. When you find the resultant of all these stresses, you get to the internal force. So if we integrate the stress over the cross-sectional area, we get the internal force. So like a normal force is equal to the integral of sigma dA over the area. That being said, I want to remind you that internal forces are applied at the centroid of the area, applied at the centroid of an area, but it's really distributed over that section or this area. On the contrary, a stress is applied at a point. A stress is related to the geometry and the load. If I increase the load, the stress is going to increase. If our part cannot handle that stress, for example, if it's a beam, I can reduce the stress by increasing the moment of inertia. Because sigma is equal to m over I times y. So we see the stress is related to the load, the bending moment, and is inversely related to the cross-sectional area. Sometimes the stress is also a function of temperature and processing. And as we have discussed on Tuesday, we have two types of stresses: an axial or a normal stress that acts perpendicular to the area, and a shear stress that acts parallel to the area. And we're going to get more into that. So the normal stress is normal to the surface. And we sometimes refer to it as axial stress, as an axial stress. And we use sigma for a normal stress. The shear or tangential stress is tangent to the surface, and we use tau for it. With the normal stress, we need to distinguish between a pull or a push, tensile or compressive. When I am pulling or acting outward on a surface, that's a tensile stress, and we usually give it a positive sign. When it's pushing on a surface, it's compressive, and we use a negative sign to describe that. Since we said the stress is a force over an area, it has the same units as pressure, same units as modulus of elasticity and shear modulus, and it is force per length squared. So using US customary units with BPSI, and using SI units would be Pascal or Newton per meter squared. Always keep in mind, even though the stress has the units of pressure, but it does not act on an area, it acts at a point. It is the internal forces that act on a surface. So we have a cut, and we do not specify a point. Yes, they act on the centroid, but actually we can, the internal force point of action may be described as the centroid, but the internal force is distributed over the surface. The stress is applied at a point. And indeed, the stress varies from one point to another over the section. We learned that a good way to describe stress is to use a stress element. And again, I emphasize the stress element represents a point. And what I am showing here is a general 3D stress element, as well as a plane stress element. And when I say plane, I mean all the stresses are acting on the plane of the board here. So we only have XY plane. We don't have anything going in the Z direction. That's why we can simplify it to the square in a case of a plane stress. For 3D stresses, you see here the general 3D stress I'm looking at a cube that is showing faces in the X, Y, and Z direction. And keep in mind that these X, Y, and Z directions are directions that we choose or make up. So the stress element represents the state of a stress at a point. And these coordinate directions are arbitrary. If I can pick these coordinate directions such that the shear stress is 0, I will be looking at principal axis and principal stresses. And you learned about principal stresses in solid mechanics. Why is it important that we identify principal stresses? That's the maximum axial stress that acts at a point, right? And of course, failure would occur due to that highest stress, axial stress, if it's failing due to a normal stress. So we want to prevent failure, or we want to make sure we are designing machine elements that are not going to fail. In most cases, the cross shears are equal, which help us simplify what we are looking at. So if I look here at the case of a plane stress, tau xy acting on the x face is equal to tau yx acting on the y face, because these are cross shears. And because they are equal, we took the liberty to call them here tau xy and tau xy. They have the same magnitude, though acting on different faces. On the 3D element, you see here I'm using the proper notation. I have tau xy and tau yx. Why? Because the first subscript represents the face where the stress is acting. And the second subscript, y, represents the direction. But because they end up to be equal, that really helps us simplify. So if I'm looking at the 3D element here, we can say that we have 9 stresses, 3 on each face, and I'm looking at 3 faces. Of course, on the opposing faces, I'm going to have equal and opposite stresses to keep this in equilibrium. But these 9 stresses could be simplified to 6, simply because of the fact that cross stresses are equal. So tau yx is the same as tau xy, tau zy is the same as tau yz, and tau xz is the same as tau zx. Please feel free to stop me at any time if you have any questions. As I said, these sessions are meant to help you refresh what you've learned in solids and inter-to-machine design, but I'll be happy to elaborate further as needed, right? Because we're really trying to cover almost a course in one session. So I know I might be going too quickly, but I'm not trying to teach you new material, but rather help you refresh and look at it from a different perspective. So please keep that in mind. And if you have any questions, please feel free to stop me. Cartesian stress component. This is what I was just discussing here. When we look at a surface, in this case, I'm looking at X, described by the normal in the X direction. The stress components are defined by 3 mutually orthogonal surfaces at a point. So you can see the normal is always going to be perpendicular to the surface. So it's acting in the same direction as the plane. So it's going in the X direction. Then I have this tangential stress that could be acting in any direction parallel to the plane. And usually we resolve it into 2 rectangular components. In this case here, one in the Y direction and one in the Z direction. So this is how we come up with these Cartesian components. Next, we look at plane stress transformation. Remember that when I pick the X, Y, Z directions, these are arbitrary. But I may or may not be hitting the most critical directions. And when I say most critical, the one that would give me principal stresses or maximum shear stresses. I really should be able to look at the stress at a point in any direction, any chosen direction. Because of that, we looked at transforming the stress from the X, Y, Z arbitrary directions to any X prime, Y prime, Z prime direction. And we focus here on a case of a plane stress, where the stresses are acting in the X, Y. So I have a sigma X, a sigma Y, and a tau XY. And we do not have anything going in the Z direction. So when we can reduce our stress at a point to a case of a plane stress, I only have to deal with 3 components: sigma X, sigma Y, and tau XY. So we can go to find the stress at any given angle phi for a plane in the n direction using these 2 equations. I can find sigma and I can find tau if I know sigma X, sigma Y, tau XY, and the angle phi. Likewise for tau, and these are known as the transformation equations. And you learned about these in solid mechanics. Now, how can we use these equations? I can use them to maximize the normal stress sigma to find principal stresses as well as principal directions. I can also use them to maximize the shear stress tau to find tau maximum. And we also, combining these 2 equations, were able to come up with the parametric equation that gave us Moore's circle, which is another brilliant graphical method to look at the stress in any direction, as well as identify principal stresses and shear stresses. So equation 313 gives me the principal stresses. And when I take the derivative, I'm maximizing or minimizing. So that's why there is a sigma 1 major stress and a sigma 2 a minor stress. And the difference between them is going from plus to minus. Also, there are 2 maximum shear stresses, tau 1 and tau 2. They are equal in magnitude, but opposite in direction. So you see plus or minus. Remember, for tangential stresses, the sign does not mean anything except direction. But for a normal stress, positive is compressive, positive is tensile, negative is compressive. Mohr's circle. And you probably learn more the importance of Mohr's circle when you learned about static failure theories in intro to machine design. Because a good understanding of Mohr's circle would help us to understand where do we stand, in which quarter of the failure envelope should I be located. So again, this is a graphical method to visualize the state of a stress at a point. So the circle represents the state of a stress for any given direction. If I can identify a point on the circle that represents the X, Y plane by showing here a sigma X and a tau XY. So let me go a step backwards. Mohr's circle is plotted on the normal stress versus shear stress for any given point. So you see a sigma and a tau. Sigma and a tau. It's written here above tau clockwise, and down here is counterclockwise, because Mohr's circle has its own special notation. So we don't go with the positive and negative that we use with the Cartesian directions, but we're showing a point above the normal axis if the shear stress wants to rotate my element in the clockwise direction. And we show it below the axis if the shear stress is trying to rotate the stress block in the counterclockwise direction. So that's important to keep in mind. So if I'm looking like at this sigma x tau x y, you see tau x y is drawn below the normal axis as if it's negative. And why is that? Let me take you back here. If we look at this stress element and I pick on this x plane, you see sigma x is shown as tension. So that's positive. Tau xy is acting upwards, which tends to rotate that block in the counterclockwise direction. You see how it's going? So that's why when we are plotting Mohr circle, we go downwards for tau xy. And you see here it's written counterclockwise direction. So this is how we get the Mohr circle notation. So as you can see, this point represents the state of stress on one plane, which is the XY plane. If I am interested in finding the stress at any other plane at an angle from the XY plane, I simply on Mohr circle would go back here again. So let's say I want to go from the x direction and angle phi to find the stress on the n direction. On Mohr circle, I would go in the same direction, but instead of going an angle phi, I would go an angle 2 phi to find that same stress. So here on Mohr circle, you see I'm going an angle 2 phi, and this point H represents sigma n and tau n that we could have also find using the transformation equations. The beauty is Mohr circle is once you construct the circle, you can answer all the what if questions. What if this angle change? What if I want to find the maximum axial stress or normal stress? So maximum normal stress, I will go all the way to the right. And here comes my sigma 1. And please note that sigma 1 is where the shear stress is a 0. That's what we learned earlier. If I find the minor, here comes sigma 2. If I want the maximum shear, I go all the way up. And this would be my tau max is at point F. And I get a tau minimum here at point G. So then the question is, how do I construct Mohr circle? There is more than one way to draw Mohr circle. One of them is to identify the center of the circle. And the center of the circle is going to be always on the sigma axis, and is so basically tau is a 0. This tau is a 0. And this sigma is sigma average. If you know sigma x, sigma y, you add them and divide by 2, that will give you the location of the center of the circle. Then I can calculate the radius, knowing sigma x, sigma y, and tau xy. I can find the radius by finding the square root of sigma x minus sigma y over 2, all squared plus tau xy squared. So this is one way of drawing a Mohr circle. Another also easy way to draw Mohr circle without doing much calculation is to identify 2 points on orthogonal surfaces, as in sigma x tau xy, and so this is 1 point, sigma x tau xy, and my other point is the state of stress on the y surface. So I have here a sigma y tau xy. Please remember, cross shears are equal. So this distance is going to be equal to that distance in magnitude. But one tends to rotate the element in the clockwise direction, the other tends to rotate it in the counterclockwise direction. If I draw a line that connects these 2 points, where it intersects with the sigma axis, this is where my center is going to be. So without doing any calculations, just by identifying these 2 points, I can quickly draw my circle. Okay. I know when we first learn Morse circles, sometimes we think it's confusing, but if you have any questions on Morse circles, I'll be happy to take it because I think it's a great tool that we can use it very quickly to do stress transformation, find principal stresses, measure a minor and maximum shear stress. Next, how do we calculate stresses? And this is what you learned in solid mechanics. So again, there are 2 types of stresses, but the way a part is being loaded is what determines how I calculate the stress. So when I have an axial loaded part, pure axial loads, I say we have a uniform stress distribution. We also get uniform stress distribution from a direct shear, as in using shearers, or as when we have a bolted connection and we are trying to shear the bolt, set in direct shear. For those 2 cases, the stress is easily calculated by dividing the force over the area. And these are the only 2 cases where we have uniform distribution. Other types of loading could be as like beams in bending and shafts in torsion. And you learned also about these in solid mechanics. So for beams in bending, I do get a normal stress. And this normal bending stress, and when I say normal, because it acts normal to the surface or to the face. So I still use sigma, and I say sigma x is equal to my over I. And if you look carefully, there is a negative sign. Can anyone remind me why do we have a negative sign? Yes, I understand that the stress is linearly proportional. So I have this distance y. So as you go further away from the neutral axis, y is measured from the neutral axis. And you learned about neutral axis in statics. When we find the centroid, then we say the neutral axis goes through the centroid or the neutral surface. And then the distance y is measured from the neutral axis in the y direction. So here the bending moment is really acting about the z-axis. It doesn't have a subscript, but this should say mz. So sigma x is equal to mz times y divided by I, but there is a negative sign. And my question is, why is there a negative sign? Opposite of the moment? No, no. The moment is positive. And if you do the clockwise, the right-hand rule, so the moment should be going like this. Z is perpendicular to the plane of the board. So if I apply my right-hand rule, this is how I get my bending moment. So the question remains, why do we have a negative sign?
Because when you bend, one side's in compression, but the other is in tension. So a positive y means a negative stress, so that's compression. The negative y means a positive stress, which is tension.
Very good. Excellent. Excellent. Correct. So as I have a positive bending moment that goes like this, you notice that the pull, which is the positive stress, is in the negative y direction, and the push, which is negative, is in the positive y direction. So that's why we have the negative sign. And by the way, if I remind you with biaxial state of stress, if I'm looking at sigma x from an MZ, we do not use a negative sign because that's no longer true. Okay, so when you did combined stresses and I have an MZ and an MY, the MY does not come with a negative sign. And just as a reminder, the I is the moment of inertia or the second moment of area. And you learned about it in statics. So if we go back to basic, it is the integral of y squared dA over the area. And of course, y is measured from the neutral axis. So first we have to find the centroid because the neutral surface goes through the centroid of the section. Beams, while primarily in bending, they are also in shear. So there are shear stresses for beams in bending. And maybe a good way to describe it, if you hold a deck of cards in your hand and try to bend it, you will see that the cards are trying to move one with respect to the other in the lateral direction. And this is what creates a shear stress. So if you cut along any section, there are shear stresses. And these shear stresses act in the transverse direction as well as the lateral direction because of cross shear effects. And this shear stress in bending may be calculated using the equation that I'm sure you've used a lot, tau equal to V Q divided by I divided by B. And I think one of the a bit confusing symbols here was this uppercase Q. And this is the first moment of the area at the section where you are trying to calculate the shear. So let's say I want to calculate the shear right here at Y1, at a distance Y1. We say we are gonna cut and look at this shaded blue area and find the moment of that shaded blue area with respect to the neutral axis. So the shaded blue area is known as A prime. If I find the centroid for A prime, the distance from the centroid to the neutral axis is Y prime bar. So basically Q is equal to Y prime bar times A prime. This is the moment, first moment of the shaded area A prime with respect to the neutral axis. So I multiply the internal forces, internal shear force V times Q, divide by the moment of inertia, divide by the width of the section. In this case, it is B because I have a rectangular section. Something that you ought to remember, the maximum shear stress for a rectangular section in bending acts at the centroid and is equal to 1.5 the shear force divided by the area. 1.5. So we have really a parabolic distribution where I got always 0 at the top, 0 at the bottom, and at the centroid, I got the maximum shear stress, which is 1.5 times the shear force divided by the area. So never, if you have a beam in bending, never just divide the shear force by the area to find the shear stress. Torsion. And you learned about torsion in solids. When I twist a prismatic member, I develop torsional shear stresses, that they may be calculated using the equation for a round bar, tau is equal to T, which is the torque, the internal torque acting on that shaft or bar, multiplied by rho, the distance from the centroid, divided by J, the polar moment of inertia. So tau is equal to T times rho divided by J. To maximize this equation, I would maximize rho. So I would replace rho by the radius of that circular prismatic member or shaft. We can also find the angle of twist using the torque. Theta is equal to T times L divided by G divided by J. Another topic that you started learning about in solids and used it in intro to machine design is stress concentration. Stress concentration. This stress concentration occurs primarily due to geometric changes. Geometric changes. They call for higher stresses that sometimes are referred to as stress raisers or stress risers. The stress concentration in rare cases also could be due to localized loading. Usually the loading is distributed over an area, but you have a very localized loading, yes, that can call for a stress riser, but primarily due to abrupt changes in geometry. The effect of these stress risers theoretically may be calculated using theoretical stress concentration factors that we refer to as K sub T. We use K sub T to calculate the maximum stress using the nominal stress. So if my nominal stress is equal to a normal force divided by the area in case of axially loaded member, I take that nominal stress that we refer to as sigma naught and multiply it by a KT to find the maximum. So we can say that the theoretical stress concentration factor is the ratio of the maximum stress divided by the nominal stress. I think you would remember seeing these charts. So here I have on the top figure. So these are available in your textbook in Appendix A15 for several types of loading and geometric changes. So I just picked two so we can look at 15.1 and 15.9. So 15.1 represents a case of an axially loaded plate that has a cut in the middle. So this cut is an abrupt change in geometry. It causes the stress to be elevated around the cut. So we know that we can calculate the nominal stress, sigma naught, by taking the force divided by the area. Uniform stress distribution when there is no cut. But around the cut, the stress could be as much as 3 times as much as the nominal stress. So we can find, using this chart, I can find a KT depending on D over W, where D is the diameter of the cut, W is the width of the plate. So the smaller this D over W ratio, the higher the KT. But you can see that easily the stress is going to be doubled. If I overlook a stress riser, I may be designing a part that will fail because I am overlooking the stress that is doubled. So that's why these stress concentration effects should not be excluded. Of course, it really depends on the material and the type of loading, as I'm going to discuss in a minute here. Another example is this part in bending. where it could be of that of a stepped shaft. So there is a change in the diameter, and this part is bending. Again, the KT is going to depend on the radius of the fillet divided by the smaller diameter, as well as the ratio of the larger diameter to the smaller diameter. That's why there are multiple curves. And I think you all recall how to use them. We start at the axis, the horizontal axis. We go up until we hit the right curve. We go to the left and read what KT value we have here. And then I multiply it by the nominal stress. We're all good? Any questions? Okay, let's keep going then. So when is it important to apply stress concentration factor and when it is not? Anyone recall that? Yeah, but sometimes we have a critical point or an abrupt change in geometry, and we say, oh, we don't have to worry about KT. You learned that in chapter 5 in Intro to Machine Design, when you learned about failure theories. If you're designing a part out of a ductile material, even though you may have a stress riser or stress concentration, when the part is subject to only static loading, loads that are not varying, static loading, you do not have to worry about stress concentration factor. Why is that? Because when you're using a ductile material, you remember it can absorb lots of energy and get into plastic deformation before failure. So even though the stress is so much elevated, at that point, it started, as it starts to deform, it will redistribute that stress into the vicinity of that point of stress concentration. And the part is not going to fail. So you started going to get see some plastic deformation, but the part is not going to fail. Again, if it is ductile material and static loading. However, if your part is made of ductile material, but your part is experiencing fluctuating loading that can lead to fatigue, I have to include a stress concentration effect. And in this case, I'm not going to be using KT. No, I'm sorry. I will be using KT to calculate a KF. So in my stress equation, I will be looking at a fatigue concentration factor. And I'm going to talk more about it when I get to fatigue. A case where we always have to look at the theoretical stress concentration factor is that of parts made of brittle material, even though they may be subject to static loading only. Because with brittle material, failure occurs abruptly. So as soon as you get this elevated stress, there is no room for redistribution of the stress. The part can fail abruptly as a result of the stress concentration. So with brittle material, whether it's static loading or fatigue loading, we have to take into consideration the stress concentration. Before we get into failure theories and fatigue, I need to remind you with our design factor. We refer to it as N sub D. And sometimes you see this D replaced by a Y or by F, like yield design factor, fatigue design factor, shear design factor. So for the same part that you're designing or analyzing, you could have multiple design factors. Before you learn machine design, in solids, you used to calculate something simple we used to call factor of safety, right? In Intro to Machine Design, we look at it at a broader perspective, and we call that a design factor, and we can define it as the ratio of loss of function parameter over the maximum allowable parameter. So it really depends on what function you're trying to measure. So you say like, oh, I'm gonna break this into two pieces if my load reaches the certain level, or if my temperature reaches that much. Okay, so you can be looking at multiple parameters. If your parameter is load, then you can say the maximum allowable load is equal to the loss of function load divided by a design factor. So if I'm looking at this equation, would you think that this design factor ND be greater than 1 or less than 1? Greater than 1. Because the reason we have these design factors, we want to account for uncertainties. So I want to make sure that when I tell my client, you're allowed to go that much, I'm not going to lose function. Even though there are uncertainties. As a designer, as an engineer, I know maybe my material is not perfect. Maybe my load is not perfectly aligned. So all these could lead to excessive stresses that I'm not accounting for. So where do I cover myself? Using this design factor. What are some typical values of design factor? Now, someone may say, oh, the higher the better. Is that always true? It can make things very heavy. It can make things very expensive. It can make things not functional, not practical, not feasible. So where do we go? Where do we draw the line? So I like what you said here for products, for specific products, right? So really we expect this design factor to vary depending on your part, how critical your part is, and the application. So I heard the 3 here. 3 is not untypical for like some civil structures. They can afford the weight, and yes, if you're designing a dam, I mean, we are hearing about hurricanes these days, and we hope everything goes well. You want to use a 3. But if I'm designing an aircraft, there is no way I want to get close to the 3 because of the weight issues, right? Even within the aircraft, I can be using 1.2 for certain components, but 1.5 for more critical components. So really, it depends. For our machine element, 1.5 is a typical design factor for just standard machine elements. Okay, but really it varies from one industry to the other, and each some are going to be dictated by the type of industry or your client, depends on whom you are working with. So this is something you're going to have to look up when you are designing special parts. But I really want you to keep in mind this understanding. N could be described as a strength over stress. The first thing I started with today was what's the difference between strength and stress. And as you can see here, strength is the material property, and stress is the one that comes as a result of a load applied to a part in certain condition using specific geometry. So a stress is calculated. A strength is an inherited property of the material. And you're going to see in failure theories, we're going to use that quite extensively. Why cannot it be just simply, I look at the strengths from the back of the book and divide it by a stress value? Why can't I just do that? Why do we have to worry about these static failure theories? And if you recall, you probably learned about 6 different failure theories in Intro to Machine Design. Correct? Did you all learn about static failure theories? Why did we need them? Why can't I just simply take the strength divided by the stress? I'll take you back to basics. When I introduced strength on Tuesday, we looked at simple tension test. So I looked at this specimen that I primarily load axially. What does an axial load do? Will develop normal stress that is uniformly distributed. Is this true for any part that we are designing? The answer is simply no. So I cannot compare the strengths from a pure axial load specimen to any general state of stress. I'm looking here at a 3D stress. I'm looking here at the plane stress. These do not compare with the uniaxial stress element of a tension test. How do I bridge this gap? Using static failure theory that we are going to discuss. The best way to look at the different theories, I borrow this flow chart from your textbook, which is figure 521. This is where I would go to help me identify which failure theory should be applied when. So it starts by looking at whether my part is made of ductile material or a brittle material. So if I use a brittle material, ductile material, which typically has or will fail at an elongation strain that is greater than 5%. I would be asking, is the yield strength of that material in tension the same as the yield strength in compression? Typically, for ductile material, the answer would be yes. Most ductile material exhibit the same yield strength, whether in tension or in compression, unlike brittle material. If you want to think about it simply, if you look at brittle material like glass, concrete, they can handle way more compression than tension. No wonder our civil engineering fellows have came up with this composite material ideas decades ago by reinforcing their concrete, because their concrete can only take compression, but it always fails in tension. So they add this reinforcement to allow it to handle tension. Right? So brittle material, definitely the answer is going to be no. But for ductile material, mostly yes. If the answer is yes, then you ask yourself another question. Am I trying to be conservative or accurate? If you want to be conservative, you are using the maximum shear strength failure theory, MSS. Which simply says that failure is going to occur in ductile material due to shear. And maybe a good, easy way to remember this, if you take a steel specimen and load it in tension, it fails at an angle due to the shear effect. So this observation helps us come up to this maximum shear strength. Is it the most accurate? No. How did we find that? Experimentally. When we sketched the envelope, compared it to failure data points, we found that this is conservative. And I'll show you a figure in a second. So if I want to be more accurate, then the distortion energy theory is more accurate. This is the one that comes with the ellipse. Since we're talking about that, let me show you. So this is a comparison of the distortion energy theory compared to experimental data. And what you see dotted is the maximum shear stress failure envelope. And I really want to take a minute to help you remember what are these envelopes and on which axis do we plot them. When I want to plot these failure envelopes, I no longer have X and Y. Like when we did the Moore circle, we had a normal stress and a shear stress. So when I'm doing these failure theories, I'm looking at two axes. What are these axes? These are principal stress axis. Principal stress axis. You are looking at the two non-zero principal stresses. This is where Moore circle comes in handy. Because if you want to know whether your part is going to fail or not, I want to find sigma 1 and sigma 2 or sigma A and sigma B, the two non-zero principal stresses, and plot them here on this chart. If I am within the failure envelope in the first quadrant, second quadrant, or third quadrant, I'm sorry, first, second, or fourth, you're never going to be here, right? Why? No. Why never here? Okay, let's read this a bit carefully. I said two principal stresses, sigma 1 and sigma 2, correct? If I'm in the first quarter, both sigma 1 and sigma 2 are positive. That's possible. It is possible that I'm going to be in the fourth quarter where sigma 1 is positive, sigma 2 is negative. That's also possible. Is it possible to be in the second quarter? Second quarter means sigma 1 is negative and sigma 2 is positive. It's not possible. And I think I said it wrong here. It is not possible because sigma 1 always has to be greater in magnitude than sigma 2. So this is the theoretical one. But it is possible to be in the third quarter because the third quarter, both of them are negative. So yes, sigma 1 could be negative, sigma 2 could be negative, but sigma 1 is still greater in magnitude than sigma 2. So you will never plot a point here, but you can do it in the first, the fourth, and the third. I want you to think about which axis are we using and make sure it's making sense. We're not just crunching number or plotting points, but we want to make sense about what we are using. This makes better engineers, right? All right, so the reason I got to this chart is I wanted to share with you the data points and show you that this dotted envelope from the MSS is a conservative one because these are the failure data points. But with the distortion energy theory, as the name implies, it's an energy theory. The points are aligned along this ellipse that we are looking at. That's why it is more accurate. So when we are designing, we are probably using the conservative MSS. When we are analyzing and we want to make sure we get as accurate as possible, then we use the distortion energy theory. In rare occasions, when the yield tensile strength is not the same as the yield compressive strength, then you're going to be using the ductile Coulomb-Moore theory. And I'm going to get to it when I discuss brittle Coulomb-Moore theory. These are very rare occasions, but they could happen. If your part is made of a brittle material, failure would occur at a strain that is less than 5%. And you still get to ask yourself the question, do I want to be accurate or conservative? If you're conservative, you're simply using the brittle Coulomb-Moore theory. If you want to be accurate, you're going to be using the modified Moore theory. And we're going to see that basically Coulomb used Moore's circle and came up with an envelope of failure. And yes, failure was going to occur for brittle material due to normal stress, but because of the fact there is a variation between tension and compression, we had to bridge that between the quarters. And I'm going to show you the failure theory in a second. But before I get to that, I want to comment here on von Mises stress. Excuse me. We always refer to von Mises stress, and many engineers, even in industry, would start thinking of it as a stress. But I want to remind you that this is a misnomer. It's not a stress. Von Mises stress is not a stress. It's simply a quantity based on a distortion energy theory that can be used to evaluate failure. What happened is we ended up with this quantity that we call it equivalent stress or von Mises stress, that we compare it directly to strength. And we started calling it stress, but it's not a stress. So always keep this in mind. When you are looking at sigma prime, it's always positive. But we know that sigma can be positive and can be negative. So how come it's always positive? Because it's a square root quantity based on the distortion energy theory. So keep in mind that this is not a stress, but it is based on the distortion energy theory. With the distortion energy theory, we calculate the distortion energy for a case of a 3D stress and compare it to distortion energy for the axial tensile specimen. So you see here this sigma y squared, or basically the yield strengths for the tensile axial specimen. And we say, oh, this in order to avoid failure, this energy must be less than this one. And based on that, we started comparing, when you take the square root of this quantity, we started comparing this to the yield. And this quantity may be expressed using different equations. And the one I'm looking at right here, you see, I am comparing using principal stresses. That's why we plot the failure envelope on the axis sigma 1 and sigma 2, principal stresses, sigma 1 and sigma 2. And yes, we want to use the two non-zero principal stresses. This is an equation of an ellipse, represent an ellipse, and illustrated here in this figure. I can still calculate my von Mises stress or equivalent stress using several equations, depending on whether I have a 3D state of stress, whether my stresses are given by sigma x, sigma y, sigma z, tau xy, tau xt, tau yz, or sigma 1, sigma 2, sigma 3. I compile these together in this table to give you here like several formulas, depending on which case do you have. And please note in this in these equations, 1, 2, and 3 may be replaced by x, y, and z. So you have a case of a general stress. You have like 6 components, principal stresses. So you're looking here specifically at principal stresses where all the shear stresses are 0. General plane stress, where everything in the z direction is 0. Principal plane stress, pure shear, and uniaxial. Of course, with uniaxial, that would be the case of the simple tension specimen. And you will see that the von Mises stress will be the same as the axial stress or the principal stress. So this proves the concept that this failure theories are meant to bridge the gap from this simple case to this complicated case. Okay. Okay, I want to come to brittle failure experimental data. So the conservative method is the Coulomb-Moore. And basically, with the Coulomb-Moore, and maybe I should also show that here, for the ductile material, you notice here that these lines where the limits are, these are the strengths of the material. So in this case, that would be the yield strength. And you notice that the yield strength in tension is the same as the yield strength in compression. So that's why I end up with a square here and a square here that are equal. Unlike for brittle material, there is ultimate tensile strength and there is ultimate compression strength. And you see that the one in compression is way higher, almost 3 times as much as tension for brittle material. And the failure envelope, similar to that of the ductile material, you have this vertical line in the first quadrant. We have the horizontal line in the third quadrant, and then you have a line that connects between the two. This dotted line represents the Coulomb-Moore, which is conservative. To be more accurate, the modified Moore said, no, we're going to continue that vertical line until a case of a pure torsion. So this diagonal line represents pure torsion. So where they intersect, we're going to stop, and then we're going to draw this line to connect these 2 points together. Now, using equations, you're going to end up having 1, 2, 3, 4 scenarios. So yes, you can use the equation to find a design factor. But again, like Moore circle, these failure envelopes, graphical methods, for us engineers are great tools because they help us answer the what-if questions. So I always encourage you to use these envelopes in addition to Moore circle. Last but not least, fatigue. You're probably tired by now. As the name implies, fatigue is weakening of a material caused by repeatedly applied loads. I almost covered one course in one session, so I know you must be really tired and fatigued, but this is going to be the last thing. Fatigue is progressive and localized structure damage when a material is subject to cyclic loading. And when we say cyclic, could be completely reversed, or could be load unload, or could simply be fluctuating. The simplest one of them is the completely reversed. So keep that in mind. Completely reversed is a special case. This is where we got the SN diagram from, as I'm going to show you in a second. Now, why is fatigue very dangerous? Because when failure is going to occur due to a nominal maximum stress when a part is subject to static loading, failure is going to occur at significantly lower stress if I have cyclic loading. So fatigue is weakening of the material because I'm no longer at the expected strength, but at much lower strengths because of the fact that I am weakening it using these repeated loads. Failure is abrupt and is sudden and is really catastrophic in many cases. We want to make sure we avoid it. With fatigue, this is not clear-cut science. There are many empirical equations, as if you noticed. There are many theories. The one that you learned in Intro to Machine Design and will continue to use here is the stress-based method, where we use the SN diagrams. Before I get into that, the SN diagram, I want to remind you that with fatigue, surface finish is extremely important. So if you have a part that's going to be subject to fatigue, we want to make sure that it has as much as possible a smooth surface. Why? Because stress concentrations are going to lead to failure. Loading, unloading, you have a minor crack, it keeps propagating until it leads to failure. And this is why sometimes smoothing a surface or removing material could enhance the strength of a part that is loaded in fatigue. So keep that in mind, which is usually not typical. Usually you think, oh, I add material, I make it stronger, right? SN diagram. In order to understand the behavior, we took this specimen, the Moore specimen, and we load it. Beam in bending, cyclic. So we go from tension, compression. We started observing how failure occurs. We learned that the higher the cycle, I want to go, the number of cycles, the lower the stress, up to a certain limit known as the endurance limit for ferrous materials. So where the curve flattens here, and please remember this is plotted on a log-log scale. Where the curve flattens, that's the endurance limit. It can handle infinite number of cycles theoretically. And as you recall, that endurance limit was like 50% for a perfect specimen compared to the ultimate tensile strength. I start with ultimate tensile at one loading, and this gets compromised. We end up with 1, 2, 3 segments for this curve. This is for a completely reverse cycles. For non-ferrous material, as shown here with the red curve, we do not have a distinct knee, and the curve never flattens. So we don't really have a well-defined endurance limit. Because of that, if I find the strengths at 10 million cycle, we can consider that as an endurance limit for non-ferrous materials. For mechanical application, we usually want to design components that can survive more than 1,000 cycles. We refer to this as high cycle fatigue, going from 1,000 to 1,000,000 cycles, right? So we want to use that infinite number of cycles or 1,000,000 cycles. So we want to use that endurance limit. Endurance limit for a perfect specimen is about 50% of the ultimate tensile strength, but we put a limit not to exceed 100 when I'm using KPSI, and not to exceed 700 when I'm using pascals, megapascal. We were able to describe these curves. If I identify these 2 points, I can come up with this equation of a line, logarithmic line, and I can find the fatigue strength for given number of cycles N, knowing A and B, and here is A and B. Please remember that this F is known as the fraction of ultimate tensile strengths. You can find it from the chart in your table, in your book, I'm sorry, and it usually ranges from 0.9 to 0.78. If you know the stress, the completely reverse stress, and you want to find the number of cycle, you can use this equation here. Again, it uses the factors A and B. In order to correct the endurance limit, we use these correction factors, Ka, B, C, D, E, F, and you use these in Intro to Machine Design. We're going to continue to use them on your first homework assignment. I want to remind you to start working on the first homework assignment this long weekend. It is not due yet, but I encourage you to work on it. Please remember, when we're doing fatigue, we want to calculate Kf using Q and Kt. You may have fluctuating stresses characterized by two important parameters, sigma m and sigma a. When you know sigma m and sigma a, you can find the fatigue stress or the fatigue design factor using modified Goodman line. There is more than one theory. I want you to focus only on modified Goodman line. Please prepare for the quiz this coming Tuesday. You're going to be ready for this Tuesday. You want to push it to Thursday? Who is for Thursday? Right, majority rules. Okay, majority rules. So we're going to push the quiz to Thursday. That gives us more time. If you have any questions on fatigue, I know I rushed through it. I'll be happy to take questions when we come back on Tuesday. Okay, have a nice, long, safe weekend. Stay safe, well, and healthy. I look forward to seeing you again on Tuesday. Thank you.
I just wanted to let you know that I'm not going to be here on Tuesday because of Rosh Hashanah. Jewish New Year's on Tuesday.
Oh, okay.
Yeah. So
Happy New Year.
Thank you.
Enjoy.
Yeah. You record the lectures right personal campus.
I did not post them because I got the impression that everyone was here.
Okay.
But
the slides,
basically like coaching.
yeah, and if you need anything, drop me a line.
Okay.
All right.
I'll be good. Thank you. I just want